Now the best way to carry out this check is to check the scheme using the 11-step guide, and when a step is not applicable, we just ignore it. So you can still use the 11-step guide. Step 1, the design objectives. Well, these are specified as life safety. In other words, you've got to extract the smoke from the shop unit using a reservoir before it can enter the atrium. So that's the design objective. Let's move on to step 2. You have to determine the design fire size to be adopted. Now we're told that fast response sprinklers are to be installed, and the convention for fast response sprinklers is to assume a 2.5 megawatt fire, 2,500 kilowatt fire, with an area of 5 square metres and a perimeter of 9. That's what you would normally assume for a building with fast response sprinklers. This is the general design fire size for these buildings. So now we know the design fire size, let's determine the mass flow rate of smoke. Now we've got 3 models available, and in this case this is the one we're actually going to use from PD7974. As you can see, it's a fairly simple model with only 3 variables. You've got QP, which is the convective heat output of the fire in kilowatts, WO, which is the width of the opening from the room of origin, and HO, which is the height of the opening. And this model is presented by the Technical Memorandum 1995, issued by the Chartered Institute of Building Service Engineers and also PD7974 Part 2. So let's put in our known variables, and what you'd have got is here an MO, a mass flow rate of smoke out the opening of 15.6 kilograms a second. That's how much smoke will be flowing out of that opening. Now there is a downstand, and this will cause more entrainment of smoke as it passes under it. And it's conventional to double the mass flow rate of smoke. So if you've got a downstand, when the smoke's coming on, if you've got a downstand, it's got to go under it. It will normally entrain air there, and normally the convention is to double the mass flow rate of smoke. That's basically conservative. So 15.6 times 2, we're going to have to assume now there's 31.2 kilograms a second of smoke coming out of the opening. Now that covers step 3. We've worked out the mass flow rate of smoke. Let's look at step 4 now, which is determining the temperature of the smoke. And this is a formula you use here. Theta equals QP divided by MC, where theta is your temperature rise, QP was your convective heat output in kilowatts, M was your mass flow rate of smoke, and C is your specific heat capacity. Putting all known variables in, you'd have got a theta value of just over 79 Kelvin. So it's a 79 degrees Kelvin rise in temperature. That gives us the theta value. Now we need to determine the absolute average temperature of the smoke using the following formula. TL equals TO plus theta. The absolute average temperature of the smoke, taking into account the theta value, the temperature of the smoke would be 367 degrees Kelvin. Now this is a high temperature, as we would expect obviously with a 2.5 megawatt fire leaving the opening, as there's not much entrainment. It's not a problem though, because the temperature of the smoke will not affect tenability in the shop, as the shop should meet acceptable travel distances. So the smoke temperature of the smoke is not a problem. It's only when it gets in the atrium where there's people having to pass underneath it, the shop will have satisfied the code using the travel distances. So it's not really a problem as long as when it comes out into the atrium. Yeah, that's the problem. Now that covers step 4. Let's move on to step 5, which is a stratification check. Now in this case, the smoke has been extracted as it leaves the shop, so this step can be ignored. You're extracting it as it leaves the shop. There's no problem there. So let's go straight on to ventilation requirements, which is step 6. Now, we know how much smoke is to be extracted, and this is 31.2 kilograms a second. However, fans are rated in metres cubed a second, so we need now to convert this to a volumetric flow rate, taking into account the fact that the smoke will be very hot and will have expanded quite considerably. And this is a formula. V equals M divided by rho 0 times TL divided by TO. If you'd have put them in, you'd have got a volumetric flow rate requirement of 33 metres cubed a second. So that's how much smoke, volumetric wise, we have got to extract. So the volumetric flow rate of smoke leaving the opening is 33 metres cubed a second. We've got 4 fans rated at 10 metres cubed a second, giving us as an extraction rate of 40 metres cubed a second. So we can be confident that the smoke will be extracted. Now we need to ensure that the containment screens are deep enough. Well, to do this, you've got to determine the depth of the flowing layer in the reservoir and ensure that the screens are deeper than this. Now, the depth of the flowing layer can be determined as follows using this formula here, where dB is your flowing layer depth under your ceiling or your balcony, and CD is a coefficient. Now, this coefficient is 1 if there's no downstand present, and 0.6 if a downstand is present at right angles to the floor. So if there's 1, it's 0.6. And don't forget, the subscript B can be replaced with an L to enable you to apply it to any smoke reservoir or flowing layer. Now, MB is your mass flow rate of smoke, TB is the temperature of the smoke, L is your separation distance of the channeling screens, theta B is the increase in temperature of the smoke, and TO is your ambient temperature, usually taken as 288 degrees Kelvin. Now, if you'd have put those in the formula, as you can see here, you'd have got a depth of 1.85 metres. That is, so when you calculate this, you should get a flowing layer depth of 1.85 metres. So that's the depth of the smoke layer. So obviously you've got to determine now, making sure that the smoke containment screen has at least that. So you might want to add a factor of safety on, for example, 10 centimetres or something. You've got to make sure that it's at least 1.85 metres. Now, we also need to determine the additional deepening as the smoke hits the forward screen. Because as smoke hits the forward screen, it will push it down. So there's additional deepening at the bottom. So your forward containment screen has got to be bigger. And this is the formula that you're going to apply it on, where your delta dB is your amount of additional deepening, your HS is the height of the underside of the ceiling above the base of the fire, your dB is your depth of your smoke layer, WB is the distance from the opening to the containment screen. Now, this is the formula to determine the additional deepening of the smoke layer. This is the formula here, where delta dB is the amount of additional deepening, your HS is the height of the underside of the ceiling above the base of the fire, your dB is your depth of your smoke layer, and your WB is your distance from the opening to the containment screen. Now, putting in your known variables, you should have got a delta dB of minus 0.127. Now, this is a minus number, which means it's out of the scope of this formula. In other words, it can actually be a known. If you get a minus number, you can actually treat it as being 0. So there is no additional deepening. So if there's no additional deepening based on this formula, you'll have to stick with a dB of 1.85 metres. But don't forget, you've got to get a factor of safety, so allow a factor of safety. Normally, they'll apply at least 10 centimetres to the containment screen, ideally more, but that's the smoke layer depth is 1.85 metres. Make sure you've got a factor of safety going down, depending on the criticalness, at least 10 centimetres, if not more. Step 8 is your stagnation check. Again, this only applies to natural ventilation. We're using mechanical extraction, so you can ignore this step. The next step is the plug holing check. This applies to both natural and mechanical ventilation. You've got to carry out a plug holing check. Now, don't forget, there's two models to determine if plug holing will occur, and this depends where the ventilator is located. The model to use when the ventilator is more than 2 metres from the edge is as follows. This is the model to apply. Now, we've got all the variables. If you insert them in, you're going to get an M-crit, a plug holing value of 10.28 kilograms a second. So if more than 10.28 kilograms a second has been extracted from those fans, it is likely to plug hole. Now, we know the critical exhaust rate, and we need now to work out how much smoke is going to leave each fan. Well, the fan is rated at 10 metres cubed a second, so we've got to convert this to a mass flow rate of smoke so we can compare it to the M-crit, and this is the formula to apply. When you put these in, put your known variables in, you should have got an M-crit or M-fan of 9.41 kilograms a second. We know the critical exhaust rate is 10.28 kilograms a second, and we've got 9.41. So in this case, we're confident that plug holing will not occur. So you've carried out your plug holing check, and that covers step 9. Let's move on to step 10 then, which is the air inlet velocity. The final check that has to be done is to ensure that the replacement air coming in through the exit doors and the automatic opening doors is not so high as to impede escape from the building. And in this case, it's a shopping centre environment with an inlet area of only 5.2 square metres. Now, the maximum velocity that you can apply with the general public there is 5 metres a second, again, due to the general public. Now we need to check the air inlet velocity using this formula here, where AI must be greater than or equal to Vmax divided by UCI. Now, if all the fans are there's 4 fans each extracting 10 metres cubed a second, it will give you a total extraction rate of all 4 running of 40 metres cubed a second. Now, if you put that 40 metres cubed a second in, you put your velocity in, which is 5, your coefficient of your fans, your inlet, is 0.6. That's your coefficient, 60% efficient. You've got an AI of greater than or equal to 13.33 metres squared. This tells you that if you've got less than 13.33 metres of inlet air to replace the smoke that's been extracted, then the velocity of the inlet air in that area will exceed the acceptable velocity of 5 metres a second. Now in this case there's 11 square metres of inlet area, which is clearly not sufficient, and more inlet area is required. We need another 2.33 metres squared must be provided to make sure the air inlet velocity is not exceeded. So that's what you've got to do, increase the air inlet area. Now that completes this step. We'll now move on to step 11, which is your post-design considerations. In this case, the situation, you're looking more at maintenance testing, making sure the system's looked after and maintained, because it shouldn't have an extract problem later on.